All right. So I've been in robotics for a while. This is my presentation on all the robots that I built. They've all been on Forth. I started out in about 1990. Started a company called Angeles Research Corp. And the idea was I wanted to build intelligent robots that at least had the intelligence of like a dog or a cat. That was my goal. So I founded this company in 1990, and I built my first robot, which was called Whiskers. This is all the robots that I built. There's actually a couple more that are on the list here, but I built everything from educational robots to military robots. And I've even built, a robot for the Hanford nuclear waste facility up in Seattle or up in Washington State. And after almost getting it complete, they canceled the order because I was taking too long. I don't have a picture of that one. That was my coolest robot. So this is Whiskers, and I sold over 2,000 of them into STEM labs from middle school to high school from 93 to about 2002. I estimated there's about 10,000 students per year were actually learning, getting their first cut in programming. They had no programming experience whatsoever, and they used our Triune language and Forth for all the programming. I developed Whiskers. I wanted to build, my concept was a Triune OS, and I'll get into the Triune OS a little bit later, but it emulates actually the way we work. If you do a search on the Triune brain, you'll find that there's the limbic system, and there's three different levels to it. There's the cerebral cortex, the limbic system, and then our reactionary, our brainstem nervous system. So I developed this three-tiered operating system language on Whiskers, and Whiskers was to be used a platform, a low-cost platform where people could go and experiment with this. Whiskers has 4 optical LEDs. You can see the 2 on the front. There's 2 on the side. There's 2 whiskers. That's tactile sensors. Each wheel has a current sensor where he could, even though it's using pulse width modulation, I had a circuit in there where I could very finely detect the current. So Whiskers could actually sense going from a hard floor to carpet. It had a microphone and it had a speaker. And so it could listen with the microphone. It could talk and sing over the speaker. After building the unit, I found that I really needed a compass for doing navigation, and I didn't have a hardware compass. So I made a virtual compass using the on time of the PWM differential between each motor. It used the 68AC11 Forth from New Micros, and we were buying the chips programmed with Forth in its PROM for $44 a piece in lots of 100. Expensive little bugger. So we had 32K of battery backed up user RAM. So from 0 to 32 was the PROM with all of our language, our Triune language. And then from 32 to 64 was battery backed up user RAM. So you could create quite a lot of programming in 32K, as you all know. At an 8 megahertz microprocessor clock, and it performed real-time collision avoidance really well. So we developed a curriculum, and the curriculum was a 10-period curriculum, 45 minutes each, where the students didn't know a thing about programming, and when they were finished, they knew how to do loops and working with this robot. So if a student told the robot to go forward and saw something, it automatically avoid that thing, even though the student didn't program it to avoid it. So it was an intelligent platform and they learned the concept of trying to program an AI type robot versus just robot that runs programs. This is an advanced Whiskers system. So this actually used two of the Triune boards, one in the base for doing base collision avoidance, and then the top one had a long range sonar and a head that moved back and forth. And then you see a collar. Those LEDs in the collar are actual sensors. They can actually detect objects when they get close to them. And what was kind of interesting about making LED arrays is the LED arrays could see much further away than just a single pair. So they could see, well past the wheels there. You can see the picture here of the Triune brain. It says cerebral cortex, limbic system, brainstem. And those three functions map to the Triune OS, which goals and learning, that's basically your outer loop in your program. That's goals and learning. Behaviors and tasks, as we had a task that would execute about 100 times a second, and you could define words, and then you would basically put the CFA to those words in this task list, and you do a fetch execute on each one of those words, and that's how you would execute the task list. When the task list is operating, the goal level pauses. So it's cooperative multitasking between the goal level and the task list. It's preemptive programming between the instinct level, which does all the sensor, it would acquire all the sensor data in real time, and also operate the motors. And if a sensor sees something, it would automatically avoid it, even without being told to do it. I'll go into that a little later. At that point in time, everybody in robotics was using the Polaroid sensor, and it was it could see out like 35 feet, but it had a dead zone, a 6-inch dead zone from its face, 6 inches out. It would not see anything. So if a robot using the Polaroid sensor was 4 inches from the wall, it would actually think the wall wasn't there. And it was really funny when I go to robotics things, and all the researchers were using these Polaroid things ringed around the base, and then if it got too close to the wall, it ran to the wall because it didn't see it anymore. So I designed my own sonar system, and basically what I did was, and this is using all in forth, basically I would ping the transmitter, and then I use an ADC, and I'd capture all the data into a 2K buffer, and I would look. So basically, if there's nothing there, what you'd see is kind of a curve going down like this. If it sees something, you'd see a blip on the curve. And so you just would measure how many, the offset into the array, and that's that's the distance. What was kind of interesting about that too is you could get a pattern. You could get multiple blips. Like, let's say you're going into chair legs. So you could actually do pattern recognition with this type of system. So I sold these mainly to universities and research people. So I was selling to Paxton Patterson and LabVolt, which are the number 2 and 3 top STEM suppliers in the country. And Whiskers was kind of winding down. The sales of Whiskers was winding down, and Legos was starting to actually take over where Whiskers was as the 90s closed out. I was trying to bring in another product behind it. So this was an erector set where kids could move the wheels to the front, to the middle, to the back. They could experiment with different architectures of the robot, of designing robots, all with this Triune brain sort of thing. Never got any traction with it. I built some prototypes, never sold one of these. Company came to us and wanted to do inspections inside industrial pipes. So this robot, those wheels are about 6 inches tall. So you can, it's like it'd go into like a 12-foot diameter pipe. The head had a camera in it that could pivot back and forth, and then it could also rotate, looking at the pipe. So it's looking for cracks inside the pipe. So we designed this, and it had a 500-foot cable, had a video camera, and they were literally inspecting inside pipes with this machine. This is Stockboy. So this was an interesting job. This is for a science museum. I think it was in Atlanta, Georgia. And basically what they wanted to do is they wanted to have a conveyor belt, a box come off the conveyor belt, and then the robot would grab the box, take it over to the other side of the room and dump the box off and automatically come back and wait for another box. So it has infrared beam on both sides of the top there. You see the black belt on the top, the wide belt, that's motorized. So what it would do is it would follow the white tape on the floor, and if you just change the tape around, you change the path, it just automatically followed that white tape. And it would just stop when it got to the end. It had a beacon sensor also, and it would stop at the beacon, and then when the box came down and broke the beam, the belt would turn on, it would pull the box onto the machine, and then it would take off and go to the other side, dump it, and then come back and wait for a new box. So that was an automated guided vehicle, called it Stockboy. Only built one of those. This is Modular Robot, Research Robot 1, and so basically using the same controllers again. This time I had to build high power H bridge because I had a little 2 amp H bridge on the board. So it was a 16-bit part. So I just removed the 2 amp H bridge and put in a socket, and then that would go to a high power board that I designed for this guy. And it's got rings of LED sensors around the base for collision avoidance. It's got an arm and a gripper. The head will swivel back and forth and look up and down. It's got my sonar in there. It also had a PC and a switching power supply inside, so that researchers could put, PC based like vision systems and stuff like that in it. Towards the end, I was trying to figure out some way to get this into consumer product. And so we came up with this idea, Bugsy the robot. And it basically would be like a Roomba, but it was a pet rather than it didn't clean anything. It was just a pet. And so that was the last robot I built with Angelus Research. Sales were dropping and I had to go get a real job. But anyway, we did build a prototype. We showed it to some people. About 97, I knew the KG Engelhardt. She was the manager of the Far West NASA Technology Transfer Center. She invited me to a conference on robotics, and I met Colonel John Blitch there, and he had an $80,000 grant to look into building man-packable robots for the U.S. military. He was with U.S. Special Forces, and so I was very interested in that. So I did a lot of work for him for very little cash, but I was really interested in it. So I built his first machine. They nicknamed it Goldie because it's gold anodized. It was kind of like a box with just 4 big wheels on it. so it was invertible. And he did a lot of work with Goldie. The military guys named it Goldie because gold anodized. And we could go out a mile with it. Had a 2.4 gigahertz 2-watt wireless video. It fit in a standard military backpack. It had to be 18 inches wide and 8 inches tall. Had to weigh under 40 pounds. So customers for this was Southwest Technical Research, DARPA, U.S. Special Forces. I even sold one to the CIA. So this is a picture. That was a prototype that you saw on the previous page. This was the the production unit. And we demonstrated at Fort Bragg. What was kind of interesting about that was, we had a fully CMOS processor running our system, and when one of the tests they were running all the robots through was how stealthy they were, and they were using night vision glasses. And when they looked at Intruder, they couldn't see it. Now, by this time, iRobot had developed a PackBot, which is the lower right there, and the PackBot had a PC, embedded PC in it, and it was lit up like a Christmas tree. So that's kind of interesting. At the time, the Kosovo War was going on, and I was the only one that actually had a robot in production, and they had a company called what was the name of it? Oh well. Anyway, it's a big, pretty good sized defense contractor. Really liked the Intruder and wanted to represent us, and they were working on a 10-unit order. But before they got the order, the war was over, so we didn't get the order. But anyway, Southwest Technical Research, that was an interesting one. So they put together an obstacle course to test all these different military robots, and they actually paid me. They considered me an expert. They paid me to come out and evaluate their obstacle course, and that's how I got connected with them. And it was really good. They had railroad tracks. They had 3 different sizes of boulders, of rocks, boulders, 3 different sizes of grass cut. Really good. And they had sand and all kinds of stuff. Well, they called me one day and they go, Don, we need to buy one of your robots, one of your Intruders. I said, okay, great. What's the price? 25 grand. That's what everybody else is selling robots for. Okay, so they sent me a PO for 25, and I built them a robot, and I called them up, said, hey, got your robot done. They said, okay, we want to fly you out, and what's your per diem? Give them a number. Sounds great. We want you to come out for 4 days and train our people on it. I said, okay. So I fly out there, spent 4 days. Now, I'd already been working with the SWRI people, so I knew them, but there's another guy that was there I was training. I think his name is Mike. And towards the end, after I was done, Mike goes, you want to go out to dinner? And we go out to dinner. He says, actually with the CIA, we're going to use your robot on a real mission. We're going to mount an arm on it, and we're going to shoot a vial into some water, a pond or something, to get samples. Oh, wow, that's cool. Oh, yeah, hang on a second here. I want to show you. There it is. Okay, give you a quick look at it here. So all the batteries, all the electronics are inside the tubes, and the wheels actually cover all of the tube, and so it's an all-surface drive vehicle. And here's it operating. So it worked well in deep sand. It could actually swim on water. Now, I didn't make a waterproof version, but with those deep treads, it could swim on top of the surface of the water. We tested on snow. It worked really well. Now, here we're doing a range test. Okay. Get back to my presentation. This is a robot I worked on in 2010. It's called a mule, multifunctional utility something or other. And this is for Lockheed Martin. And I worked on, we had an FPGA controller for each one of these arms. Each wheel, you notice, is on an arm, and that each motor was a 6 kilowatt motor. So it was 600 volts at 10 amps. And I worked on the FPGA. There was is an Altera FPGA with dual processors in it, and it was networked using standard networking system, Ethernet. This was a military man-pack robot prototype I built. Here again, the concept of all-surface drive. So all the electronics and batteries are in the tread units. It's a final version that we made. The treads, you see the big black knobs, there's two on each side. If you unscrew those knobs, that entire tread comes off. So you could have two soldiers, man pack this robot in. This is the last robot I worked on. This is for Redwire. This is a NASA robot, and this one is going to be the first 3D printed beam in space. It's a 10-meter beam. They're going to print a 10-meter beam. The lower right there, you see that kind of white sheet. That's a simulated solar film. So as it 3D prints, it's going to unroll the simulated solar film. This is a technology demonstration project for NASA. On the other side, you see that there's just a lattice beam. NASA wanted us to test some characteristics of the beam, like if they're going to wiggle the spacecraft and see how much it flexes and things like that. And let's see. That's this one here. But you see that it's extruding as it 3D prints, it's extruding or unrolling the solar film. I designed the computer for this one, and I also designed the high-speed, high-voltage H-bridge motor driver circuit. So it's going to extend this out to 10 meters, and then there's going to be a robot arm that picks up the 3D printer and puts it on the other side. So now that it's got one side done, it's going to zoom in and it'll show you how it's going to pick up the 3D printer and put it on the other side of the spacecraft. So my computer controls the arm and the 3D printer. We have two dedicated FPGAs, one for the arm and one for the 3D printer. Now, they did find that they needed some high power inverse kinematics towards the end, and they had to add another processor to get the processing speed for the inverse kinematics. So you can see that the arm moved it over and now it prints the other side. Okay, let's see. So that was Arcanet. So this is the Whiskers board, or the Triune brain board. It's got two 24-volt, 2-amp pulse width modulation channels. I have an optional 48-volt, 40-amp high-power driver board. Oh, hang on one second. So anyway, so it's got two tactile sensor inputs. It's got a speaker, microphone, motor current monitoring, single serial port. It's all Forth based, Triune OS, and it even has a network port, and you can network these boards together. So the Triune OS in silicon, you got the cerebral cortex, which is a goal level, and that's basically your main loop. That's it's equivalent to the outer layer of the brain. So what you're going to do is you're going to put code that is analyzing the environment. It's non real-time type code. It's more analyzing type code in the cerebral cortex, or the outer goal loop. The limbic system is your that I call the behavioral task list, and that's where you look at behaviors. So let's just say the left and the right whisker gets hit at the same time. So you make an if behavior. If left whisker and right whisker, what I want to do is I want to back up 1 foot. I want to pivot 90 degrees, go a foot over, pivot 90 degrees, and then terminate the behavior. So by putting these behaviors in a prioritized fashion, so like tactile sensors are more reliable than optical sensors. So you would prioritize the tactical sensor first, and then the next behavior down would be, let's say, the optical sensors. I got both side sensors see something, both front optical sensors see something, and you program different behaviors. Now, when the behavior is executing, it's cooperative multitasking. So the goal level ceases to function and waits for the behavior to terminate. And by doing this, it makes the robot, it's really simple programming, because you look at a situation that the robot gets into, what does the sensor see, and then make a behavior for that. And now you've just taught the robot a new way to deal with the situation. So it's event driven. It's based on the situation. You're not programming it. Like when you use this system to program a mouse competition, you program the algorithm into it. You don't sit there and look at the maze and tell it when to turn and all that sort of thing. And a mouse competition was like 1 page of code. It was really simple. The instinct level, even when the behavior takes control, the instinct level is still working. So let's just say that it's backing up and the left whisker hits something, the instinct will take over just as long as that sensor is being activated, and then it will terminate. So instinct level is very primitive. I touch something hot, I pull my arm away as a reflexive response. So instincts are reflexive response. Each sensor in the robot has 4 or 5 registers. So for example, the optical sensor has a register for the LED on reflectance value, LED off value, and then the third register is the instinct level subtracts those two, puts it in the third one, which is the reflectance. And then there's another register called the trigger level. If the reflectance is, say, over 10, maybe you put 10 in the trigger level, then you get a motor override. So maybe, and you have a register for 9 different motor combinations, motor, forward, reverse, that sort of thing. And so you can build a lot of intelligence in the instinct level, but it's very dumb. It just reacts. So those 3 levels working in tandem creates a very intelligent machine. I called it the Triune OS because I actually had built the 2 levels, just instinct and goals. And when testing, I needed I need the behavior level. So I added the behavior level. And then I went to a trade show and I was talking to a biologist scientist, and she goes, well, that's the Triune brain. So after that, I called it the Triune OS. So here's how it maps. We talked about this before. So here's the multitasking AI model. So the dashed line is, that's anything above, that's your foreground. Anything below it is your background tasking. So this is how they interact with each other. So data goes up the instinct level to both the task level, task behaviors, and the goal level. Commands go from the goal level down, and that's how they interact with each other, and that's how they basically they map. And so we also, you notice we have priority. So instincts are highest priority, the lowest intelligence. Tasks and behavior like medium priority, medium intelligence, and the outer layer is the lowest priority and highest intelligence. So the future that we're working on, and Dimitri is working quite closely with me on this. We're developing the Core 1/4 on FPGA project. We're going to be putting the Triune OS and language on the Core 1/4 computer. I will be, I've already bought the parts. It's going to be many, many months out, but I am going to build a 4th computer development kit for people to experiment with the 4th computer and the Core 1. The Core 1 being the processor. The 4th computer means it includes the outer interpreter and compiler. So that's how it differentiates. I do have a new Whiskers board that I'm working on. We're calling that the AI bot. That uses an ESP 32, but we will be able to incorporate, maybe network the boards together, or maybe I'll make one board at some later date. So we will have an AI bot complete kit with 3D printed parts and that sort of thing. I like to build a walker one of these days. And I was also thinking a 4th computer touch tablet would be kind of cool. Dimitri and I are both very interested in AI, so we're going to be putting a lot of AI on the 4th processor. And here's a quick update. Almost done. Here's a quick update where we're at. The outer interpreter is done. We added a 32-bit multiply and divide words. Divide was really challenging. I added pulse width modulation, 4 channels of it. So, because, going to be using this for robotics, so it has to control motors. Halfway done on the SVI. So the task right now is implementing the compiler, the 4th compiler. And then the final task is we've implemented some basic core 4th words, but we'll need to kind of round out the word set for all the basic words. And then system testing. And one of the key features of our system is we don't use any proprietary IP blocks. Everything is source code. So you can copy and paste it in Altera, Xilinx, Microsemi, Lattice. It just copy and paste the source code and you can run with it. All code is behavioral system Verilog. We don't, even the outer interpreter and the compiler is in system Verilog. So they're going to be running really fast. I know that's unorthodox, but it works. We're doing it. So here's where we stand right now. We're using 3,360 LUTs out of 5,280. So we are only using 64% of a $5 FPGA. And so I'm really happy. The goal wasn't to get it small. The goal was to we wanted readable high-level code in System Verilog, and that was priority one. Making it go faster or smaller was secondary, and it's just going to wind up where it wound up, and it wound up being very efficient. So we're pretty proud of that. We set up a Facebook page to work on this, and the link is down below there. I'll copy and paste the link into the chat so you don't have to read that. So we're calling it AM Robotics because this isn't just a fourth group. We have a lot of discussions on AM Robotics because that's what we want to build. We want to use Forth for everything. We want to use the Core One project for everything. So you're welcome to join. I'll put a link in the chat. Is there any questions?
Yes, I have a question.
Hi, Dimitri.
Hello, hi, Don. Apart from Archinaut 1, do the other robots that you showed run Triune OS?
They all do.
They all do? Wow, okay. We'll run Triune OS.
Yeah, the Triune OS is actually very simple to implement on a regular micro. It's like it's a page and a half of code or something. You basically create a counter timer with a periodic rate to create the instinct level, and then you create a timer from that, just a counter. Like maybe you have that running at 1 kilohertz, and then every 100 hertz you call the task list.
Very straightforward. And what do you think is the next big step for the Triune OS?
Well, it's going to be implementing it on the Core One and the fourth computer. And what's going to be nice about that is because we're on parallel hardware. It's really, I was emulating parallelism in a sequential machine when I created the Triune OS, because it's a kind of a parallel algorithm. And so it's going to be really nice to implement on an FPGA. We could make the task list, for example, not interrupt the foreground code if we want to. We could have a separate process. I think that is an important feature. I think we might wind up doing is actually having two task lists, one that interrupts, because the algorithm of executing a behavior when something happens, and say you're doing collision avoidance, that's part of the algorithm. But we may also have a second task list that runs in parallel to do multi-processing sort of things. So I'm really excited about working with you on that, Dimitri.
Yeah, look forward to that.
Don?
Yeah.
I think I've mentioned before, actually, the cerebellum needs to be added into your model in one layer or another, however it is, because the cerebellum is where an awful lot of the algorithms for actually doing the motor cortex works with the, sort of sends commands to the cerebellum, and the cerebellum actually goes and gets it done.
Yeah, so so that's called the goal. We call that the goal level. That's where all the high level thinking tasks will be occurring.
Yeah, one of the things that's interesting about it is that the cerebellum has a very, very organized structure that's worth looking at just in itself. My other question, what do you think of BattleBots? How does yours compare with the BattleBot?
Well, I love them. So I have a funny story about BattleBots. So I was the technical VP of the Robotics Society of Southern California from about 1990 on. And we were contacted by, I think his Mark Thorpe. He was on the set that did all the Star Wars movies, and he wanted to create what do they call that? Yeah, it's basically battle bots. He had a different name for it. And so we went up there to the very first one in San Francisco, and we were up there. We're talking to him. He said, "How would you like it if we did an autonomous demonstration?" Because I was a fourth guy, and I had my Triune OS stuff going, and the president of our club was a C guy. So he and I were always battling. Our bots were always battling to show which was better, fourth or C for robotics. And of course, fourth is better. And so we spent the next year developing these robots. I named mine Spike. It was a pretty healthy robot, and it weighed about, I don't know, 60 pounds, had spikes all around it, and had a sonar. It could look and is looking for the other robot. And I was up there just before the event. I was programming the robot, adding some new behaviors and stuff like that. And I didn't leave the charger in while I was doing this. And so Spike saw the robot and bolted out, charging towards the robot, and stopped. He ran out of juice. And then the other robot comes across. Now it was written in C, so it come across like a foot, and then it would stop and look around and go, maybe 6 inches, and then it came up and it touched Spike. That was the last of the autonomous robots and combat robots. Mark Thorpe said, "No, we want parts flying. Sorry, you guys are gone." Anybody else? Oh, I was going to put
So the other robot was destroyed when he touched yours?
No, nothing was broken. He just touched it. He just tapped me, and he didn't have any armament or anything. That's all he did. So,
okay.
The crowd was there to see parts flying, right? They couldn't care less about AI or robotic control. It was pretty funny.
That's great. Thanks for this story.
All right. I'm going to put the link in the chat. Okay, the link is in the chat. So if you're interested in AI and robotics, or you're interested in the Core 1 and the 4th computer project, you can go to that page. That's it for me.
All right. Thank you very much, Don. At this point,
Do you have more
I'd
questions? I have
Go
one more
ahead.
question for Don. You said the outer interpreter is done. How many characters can the words be?
Any length. I think we have a max of like 64. It's a parameter, so you can set the parameter to whatever you like. I think 64 characters would be good enough. Dimitri tested the search algorithm. It could test 10 million words per second. Pretty fast.
That's great.
Yeah, and the compiler is going to be also written in system Verilog's, so it's going to compile, as fast. It's going to compile in probably just a few clock cycles. Now, what's kind of interesting about that is you could have source code sitting out there, and you can compile on the fly while it's running. That might be interesting.
I was thinking that you might do a byte coded thing, and that what comes through is like partially compiled on on the host, and then partially compiled, finally compiled from bytecode actually on the processor itself, and that would save space.
So yeah, so we have what the interpreter is working, and so each opcode, you know, like right now, I think we have it set for eight bits wide. So you could, you know, you could take those defined codes, and you could write code, and you could have a, you know, you could send them over the serial line. You could have a special word that just, well, I don't know, maybe you have a word that says compile, and it just says that all the characters coming in are bytecodes, and it will compile it into memory, and then you execute it. You could do stuff like that. All the source code is going to be available. So the idea is you can take our core system when it's fully operational, and you will learn system Verilog. When you look at the code, it's very simple. I can go through the code after the meeting if you want to stay on Zoom. I've gone through the code before. I know a lot of people wouldn't want to sit through it again, but any new people, I can go through the code again. And Dimitri also could make comments, because he's been instrumental on this project. He's done a lot of the coding.
I would love to see that. I don't know if we can do it this time, but I would love to see that.
Yeah, we could do it when the meeting is officially over. They always let people hang out, so we'll do that.
Great, thanks.
Great meeting, Kevin.
I want to point out that SVFIG is available 24/7 with the same link and password. So you can come to this room and talk about whatever you care to. Don, would you like to do another presentation? You do the code within the confines of the actual meeting, or would you rather just do that today after we the reporter?
No, we would be happy to. This would be a joint effort, probably if Dimitri's available. If he's not, then I'll do it myself. But yeah, we could take up a full slot just going over the code, and be very happy to do that more thoroughly. You know, I'll just kind of run through the code briefly today to kind of give people a flavor for it. But you know, there's a lot to talk about and explain. So if you want us to do that next time, that'd be good.
It's a deal.
Okay.
I want to apologize to Bob for abruptly ending his talk, but Bob was warned in advance that there was a hard break, and I didn't want to shortchange on, because we had already done that once, and completely pushed his talk from last month to this month. So thank you for your patience, and thank you, Bob, for your patience. And I'm sorry to be the stopwatch Nazi. You should see on fourth day. It's much worse. I think it was Clausewitz that said no fourth meeting agenda ever survives contact with the actual meeting. But that's.
Let me mention, I put a link on. I'm going to be around 3 Mountain Daylight time, 2100 British Summer Time, and I put the link on there. So anybody want to go and expand a little more on what I went through very rapidly, including why functional programming or interest in it. One of the things is it really is a very, it runs the web. It runs the web, and they make money. And those are the two things that impressed me most about the conference.
It reminds me of my youth when I used to work in a calibration lab, and one of the technicians set the time on the cesium beam standard to daylight savings time. But we digress. So British summertime is kind of useless. I generally quote the time in Zulu or Greenwich Mean Time or whatever you care to call it. They're all pretty much the same actual standard.
Well, I like the fact that somehow we call it daylight savings time, and somehow it's very British to call it summertime.
Yeah, well, I think it was during Jimmy Carter administration in the 70s when they set permanent year-round daylight savings time as an energy saving measure. And first of all, it was dangerous, hazardous, and caused numerous other problems. Second of all, it cost more in energy. So there you go. I guess there was some law to that nationwide again that was in the pipe. I haven't heard anything about it since then. This was in the last month or two. I guess it went away. If no one has any actual meeting business, I'm going to ask Brad to unceremoniously stop the recording. We ceremoniously start the recording and unceremoniously stop it, I guess.